This video is on linear codes. Example of linear codes would be Hamming codes. These types of codes are denoted NK codes, or as you can see here, bracket N, comma K codes, where N is the length of the code words and K is the dimension. When you are working with linear codes, there are two matrices that you primarily use. There's the generating matrix, G, and H, the parity check matrix, where G is, or has the form IK, where this is an identity matrix that is K by K, and is part P over here, which is non-identity matrix. The P is the part that allows you to correct errors. It will be N long, or have N columns, and be K, have K rows, or have a height of K. The H, the parity check matrix, will be similar but not the same. H has the form negative P transposed, and then the identity matrix that is N minus K. So it has, as you can see, the same length N, however the height will be N minus K. We can change between G and H as necessary, depending on what we're trying to solve for. We'll flip back and forth between them. So for example, if G, the generating matrix, is this matrix here, what is H? Well, first, what do we know about G? We know that G has the form identity matrix of K dimensions and P. So therefore, since the identity matrix comes first, I just labeled what I could find of the identity matrix first on the left side of the generating matrix. As you can see, I marked it in red. P will be everything else. I also noted that K equals 2, the height, 2 rows, and N equals 4. There are 4 columns. So what form does H have? H is negative P transposed, and then the identity matrix that is N minus K square. So what I did was I took the negative P transposed first. Over here we have P, normal P. Remember from linear algebra that when you transpose a matrix, we take what is the first row and make it the first column. So 0, 1, our row, would become 0, 1, a column. And I got that negative because this is negative here. And then our second row here in our P is 1, 0. Therefore, our second column will be 1, 0. And again, the negative just comes from the negative out front here. The rest of the parity check matrix is just filled in by an identity matrix. How we figure out how big that identity matrix is we want the identity matrix, remember from up here, to be N minus K, which also happens to be the height of the parity check matrix. Therefore, since we can see that the height is going to be 2 because the height of P transposed is 2, therefore the identity will also be 2 by 2. Just so you can see that it works out, I have N minus K equals 4 minus 2, which equals 2, so you can also calculate it that way. And N is still 4. N was 4 for the G, N is 4 for H. However, since we are working in binary, which means we're working mod 2, Therefore, all our negative ones just turn into positive ones when you add 2 to them. You're working in mod 2, so therefore H, our parity check matrix, is this here. Also want to note that although I put a line here to separate P and I, that's mostly for clarity, so you can see what's going on. With H, the parity check matrix, you don't actually need that line. You can also go from H to G by labeling what you have. This is P transposed. This would be your identity matrix. And therefore, if you take P and transpose it again, or take our P transposed here and transpose it back, you can put it back into P form. And then just put it second after the identity matrix. So you can go back and forth either way by just labeling what you have.